in my PhD here, I had the dependence in this very room, about shape modeling using Bayesian methods. And just to give you a feeling for how things have evolved, 30 years ago, MCMC and all that was starting to get traction. But 20 years ago, in order to have a live demonstration with MATLAB in this room during the defense, we had to draw an Ethernet cable out through a window and in through a window here down to the computer so that the MATLAB license would be able to be accessed. The projector was sitting where I think Rasmus is sitting now, on top of John Knud's part of computer programming, just to prop it up a bit. So that was 20 years ago. So things have evolved a little bit. So I'm very happy that after I left in 2010, that this Bayesian thing has still going here and going strong. Or could be stronger, but at least it's something. So currently I am in Edinburgh since 2016, working on software and spatial modeling methods. So it's a mix of random field theory and computational methods and software engineering to try to get the theory usable by practitioners. So this talk is a bit about everything. So I'll show you just the highlights of some things. So first of all, very briefly about spatial dependence modeling using stochastic partial differential equations. I won't go into the details of that at all, just to show you the basics. The main idea there is that instead of trying to specify the covariance between the values at different locations in space, we specify a precision operator for stochastic PDE, which, if you've seen the theory for stochastic PDEs, seems like a horrible idea for practitioners, but it turns out to be actually easier. When you're building complex models, it's easier to build complex models using those, and I'll still understand sort of what they're doing. Then I'll talk about the inference methods and why we use INLA instead of MCMC. Where INLA is a optimization and integration method instead of Monte Carlo. And that leads into the software interface and some of the design choices in that. And finally, I have an example of a point process model where we apply the software. I also have another example, but I'll probably just skip that one. So, spatial random fields. So this is the kind of things we want to be able to model, where things vary across space in some generally random way, either because it's genuinely random or because we simply don't have any useful covariates or don't have enough useful covariates to model the underlying process properly. And down there in the corner, you see a little formula, which is the stochastic PDE. So in this case, it's a special case of the Whittle model that generates Matin covariance models. So the Matin covariance family, which is quite widely used in spatial statistics, has this property that you can write it as solutions to stochastic PDE driven by a white noise process. So in this simple case, that's nice. But we'll see later why it's useful from a computational point of view to be able to do that. But also from a modeling point of view, if we have data on a globe, then if we were to model with covariance functions, we would have to come up with positive definite functions on the sphere. If we model in functions on a heart muscle, then that's not a sphere, so then it's even worse. So what do you do? Well, if you just apply that stochastic PDE on the surface you have, then you get a valid model, if the surface is smooth enough, but the sphere is certainly smooth. So instead of trying to come up with these covariance functions, we just model this locally by saying that this describes the local behavior of the dependency structure. And then if we want more complex models, we change the operator. So here we have something that could be linked to some kind of pollution transport in a weather system or something like that. But the nice thing is that the model is completely locally specified. As long as we have the local dependency structure, this anisotropy, then we automatically get a globally valid model. Whereas if we did this with covariance functions, we would have to struggle a lot and probably end up having to solve a PDE somewhere anyway, or compute the eigenfunction or something. So specifying models is easy, but estimating them isn't. So what we do is that we take these fields, we represent them as sums of weighted local basis functions, where we then have to figure out what should be the joint distribution of those weights in order for the combined function approximation to have the intended properties. And you then turn to the PDE literature and find out how do you numerically solve PDEs, and then you just apply the same methods, in this case finite element methods, and out comes this inverse covariance matrix Q, or the precision matrix. So this tells us how to construct these models for any choice of basis functions. As long as we have enough basis functions to represent the variability of the function, then this tells us how to construct the joint dependence structure. And if we then have local basis functions, then we get sparse matrices. And that's really nice for computational reasons. The computation simply goes faster because we can take advantage of the sparsity. And when we then add observations, so we have this random field here called U, and then we have observations Y, which are linear combinations of these. Simply, we evaluate it at a point, or possibly integrate over some region in space. And then the dependency structure for those weights. Then we get our observation model and our prior model for the random field. In Bayesian setting, we would also have prior distributions on the parameter kappa, and there's also a hidden precision scaling parameter that I didn't include in the slides, but should be there. Q should be scaled by some common factor. Then we can work out what the conditional posterior distribution is given those covariance parameters, because the conditional distribution in the Gaussian, when you have Gaussian additive noise, is still Gaussian. So it's just a rewriting of the expressions you would normally write down with covariant matrices, and it's just doing the block transformation and turning it into precision matrices. So for the posterior precision, we just add a sparse matrix depending on where we observed the field, and then we solve a linear system to get a simplification. So kriging in the spatial classical setting is just done like this when you're working with precisions. Okay. So if we do that, I click like this. So on the left, we have a true field, and we have then simulated data for observations at the black crosses. And then we try to crank the handle and estimate everything based on the information in those points. And we get the posterior mean in the middle and the posterior sample to the right. So one thing to note is that the posterior mean is quite a bit smoother than the truth. And if you only saw the mean, you would probably think that you've oversmoothed. But that's not the case, because the samples actually look a lot more like the true one. So especially when you're thinking about Bayesian things, just because it's so easy to do in the Bayesian setting, you should always think about what is the generated values from the model, not the point estimate. Because the point estimate has a radically different structure than the truth. So anything non-linear you compute from this in terms of smoothness over space or something should not be based on the mean. It should be based on the samples. So what we end up doing here, even though we compute analytically, or at least conditionally analytically, the solution, we would often still produce samples, because then we don't have to worry about whether it's linear or not. We can just compute whatever we want based on the samples, as if we had done them same. And it's such a fine resolution of this model that you probably hardly see it. But on the lower right there, you have a triangulation of space defining these local basis functions. So we have lots and lots and lots of small basis functions there. So how do we make this work for people that don't know the theory of stochastic PDEs, which is essentially everyone? They started out, so this was Håvard Rue and his colleagues in Trondheim in the early 2000s, and they were trying to make MCMC fast for these types of models. But we didn't have the SPD models then just Gaussian marker random fields, which is this sparse precision matrix models. So they made a library called gmrflib that can do the Gaussian marker random field calculations quickly. Then they developed INLA, which is this integrated nested Laplace approximation method, which I'll talk more about, which uses this gmrflib library internally, and that's still being developed now. But the idea there was initially to do fast MCMC. So to do fast MCMC, you can need good proposals for some value of good. And what then happened was that they realized that when they come up with these good proposals, the bias in the proposals was smaller than the Monte Carlo variance you would get if you did the MCMC. So you just skip the MCMC part and just use the proposal. And that's, of course, much faster. So they sped it up by sort of orders of magnitude more than they had initially intended. So that's now not always the case for complicated models nowadays, but it's still usually the case that if the model is amenable to using INLA, it will be faster than the same model run with MCMC. But then there are some models that you can't use the methods for, and then you still need the MCMC. So of course, how do you use a C program doing this? Well, you write lots of configuration files telling it what to do. No one can do that, so they had to write an R package that can write the configuration files for you. That was quite a quick decision that they needed that. And soon after that, we added these stochastic PDE models, because it's a nice way of constructing Gaussian marker random fields where you can interpret this more widely in continuous space. And recently, there have been more updates to it where we added more of the things that we knew that in theory was possible, but now is possible in practice, like these fractional operators for the PDEs. So you get the whole of the Natan family and not just a small subset. Also, space-time models with interaction between space and time in the covariance structure. We figured out with David Bolin, who also did his PhD here, how to compute joint predictability regions. Like in space, you have an excursion set somewhere, and then figuring out the uncertainty about that and uncertainty of contour curves. And then we had added so much to INLA for the spatial models that specifying the models again was a bit messy. And also we want to do point processes where the likelihood is messy. So we had to write a new package that is an interface to INLA. That was initially intended just for point processes, but then expanded to general spatial models and then almost all of the INLA models. We're still not entirely there, but almost. And last year, I finally extracted the code for actually doing these finite element calculations so that people who use the SPD models, but not INLA, can now use them without having to install INLA, because that's a whole another story. Again, David became very productive and has figured out how to do these types of models on metric graphs. So when you don't have a subset of R2, but rather a network or some kind of processes on the network itself, on the edges. And another interface, this time an interface to INLA and inlabru. So it's an interface to an interface to an interface to an interface. Yeah, something like that. With software all over that. This was built by geoscientists in Bristol, who wanted an easier way to specify the model or write the code for it. So that you have graphical interfaces where you can experiment with things and build the meshes and construct a model, and then it can tell you what the code is for doing that. So then you can go off on your own and modify it and do some more things. So that's quite a new package that is still being sort of worked out the bugs in a bit. So practically speaking, the models that can be run in INLA is quite large, or the set of models. Essentially is the Bayesian version of GAMs, so generalized additive models, where each component in the model has some latent Gaussian structure. So it might be a spline model where the joint distribution is a Gaussian process, or just a Gaussian process in general, which is really what this does. You can have just pure random effects, etc. But it does this in a Bayesian way without using MCMC, which means that it's typically much faster than MCMC. You can also define your own models, which it used to be just possible through writing R code, so it was a bit slow when you run it, but now you can also write C code. And if you're sneaky, you can write C++ code, but it's all by that C code to make it easier to write the code, but it's still run fast. So many of the new things have been implemented in that way, which means that they don't have to be added to the package itself necessarily. You can run them independently without having to have the help of Hova all the time when developing your things. And then we have inlabru, which has simplified things a lot. And I'll show you an example of the code in a bit of how much simpler things are. But the idea behind it is that we want to have an easy way of specifying complex models without making the simple models more complex to specify. And if you try to write a software interface, you will know that that's not necessarily easy, but we've tried. So that things should be, things that can be similar to INLA are similar to INLA, but things that shouldn't be similar to INLA because they're too messy, they are not the same as INLA. And this allows us to specify more complex relationships between your data and the effect of a component. So if you have a spatial model, you might have a spatial covariate that then needs to be evaluated at specific points. And if you're running a point process model, as you'll see, that will involve an integral over space using a numerical integration scheme. So you won't know what points it needs to evaluate your covariate at. So you have to just hand over the covariate and tell it that this is in space, please do something with it. And hopefully it will do the right thing. You can also specify multi-observation models. So if you have the same underlying spatial structure, but you observe it in different ways, for example, here you have the actual locations of the disease cases, but over here, you only have aggregated counts, then you can just specify, oh, this is my observation model, this is another observation model, and I have the same underlying components giving the effects of everything. So in INLA, you can also do that, but it's quite messy because you have to rearrange your data structure, but it's predictable how you need to do that, so inlabru can do it for you. So this is almost the same slide as before without the Gaussian marker on the field. Now, with the added complication that the observations don't have to be Gaussian additive models. Then it can be anything that INLA knows about, or inlabru knows how to fool INLA into computing without INLA knowing about it. That is what the point process models do. Because they basically piggyback on existing code and just turning off some checks. For example, counts typically have to be integers. The point process doesn't care. It just thinks in a different way. But this is essentially the same expressions as the Kriging equations I had before, except that now it just looks at the posterior mode, what does the low posterior density look like? And it turns out that it looks pretty much locally like a Gaussian. So we approximate it with a Gaussian, and we can find it through Newton optimization. And as a byproduct of that, we get the mode and the precision matrix, because that's just the negative Hessian of the log posterior density. So it all works the same, really. And then we can do INLA, which means that we want to integrate out the latent Gaussian variables. So going back even further than 30 years, 40 years, 80s, what did Bayesians have to do? They had to calculate things by hand and analytically, or with very simple computations, because they hadn't really, except in a few special cases, discovered MCMC yet, not in the general cases. So one of those methods that was used was Laplace approximations. So what you do when you integrate over something, you then find the mode, you compute the Hessian or the logarithm of your integrand, and then you approximate the integral with the integral of the Gaussian, and you know the normalization of that, so you know what the integral is, because it involves the determinant of that Hessian. So the problem with that is that it doesn't solve the whole problem. It gives a good approximation if you integrate out these latent variables to get to the covariance parameter posterior densities. And this is just a clever way of writing a Laplace approximation. So you just multiply with things that you actually already know, and then you get the answer. But if you want to get the marginal distribution for the latent variables, then that Gaussian approximation itself isn't good enough. So therefore, they added this numerical integration step with another, well, it used to be another Laplace approximation, hence the word nested, integrated nested Laplace approximations. But from about last year or 2 years ago, they changed the method. So now it's variational Bayes instead. So instead of doing another Laplace approximation for the marginal distributions, they do a joint variational Bayes approximation with the Markov-Randolph field for the whole latent field, conditionally on each integration point theta. So we integrate numerically over the covariance parameters, but it's a joint Gaussian approximation for the latent variables. And from there, you then get the marginal distributions. And also, this has been adapted to then produce samples from the posterior distribution that takes into account both theta and the latent variables. So when building an interface to this, so the INLA interface was built to be as similar as possible to existing frequentist packages. Make it an easy transition for people who are used to those packages. So you have covariates, you just specify your covariate. If you have some kind of random effect, then you have an F function. So when it says F in INLA, it means that it's some kind of random thing. It may have no structure, it may have lots of structure. So it might be just independent random effects, but it could also be a spatial random field. But just as in ordinary software for these things, the name of the component is the same as the name of the input data to it. And that's not always a good thing, because if you have like elevation and the effect of elevation, they're not the same thing. And often in the output, you get just it says elevation. It doesn't say beta for elevation usually, but it probably should. So to allow some more flexibility and also to allow computed values more easily in the inputs, in inlabru we split it so we can specify a name of your component, which is basically used as the effect name, and then you have the input to it, which is the value of your covariate, or just spatial coordinates or something like that. And that means that you have to, you don't have to change your data structure just to change the name of your component anymore. And you can have two different components using the same covariate input. And that can also be quite handy. And then there are shortcuts to make life easier when you just want the standard usual thing. And then you get the effect of a component available to you in the predictor expression. So usually we just have linear effects linear additive effects. So we just add all the components together. But very often that's not actually what we want to do. We want to do something slightly different, but still based on the component values. So we compute the mapping between the inputs and the effect of a component. And if that's a latent Gaussian one, that's just a linear transformation, but it's a transformation that we don't want to have to keep track of manually. So that happens for us. And we need a way to specify for new models, how should you map these latent variables to an effect? What basis functions should you use? Should you map it in some other way? And now we need non-linear mappings. So there's a whole collection of code that just deals with reinterpreting a covariate input into which value of the effect does that correspond to. So if you have a set of latent variables and you have your covariate values, it tells us how do you combine those two to get an effect value. And in the simpler case, that's just a linear mapping. So most of these are linear, but there's at least one of these, the GRU mapper log sum x mapper, that says, oh, take my latent variables, take the exponential of them, take a weighted sum of them, and then take the logarithm of them. So that's something that is necessary if you want to do aggregated Poisson counts properly, where you have an intensity for space, and you want the intensity or the expected value over a region in space. You want to integrate over space. Most of the traditional code for this has just ignored the problem and integrated on the logarithm scale, because that's where you have your linear predictor, so your integrating is still linear. But you should really be integrating the exponential of the linear predictor and then taking the log afterwards. Then you no longer have a linear predictor, but you do have a predictor that is roughly linear. And that's enough to make this work. Because what inlabru will do is to say that, okay, I'll take your nice nonlinear function, I will linearize it, run INLA, and see if that agrees with where I linearized it. If it didn't, then I move my linearization point, and I keep doing that until the linearization point agrees, and then I have a sort of the optimal, in some sense, linearization. And crucially, it knows how to convert between triangulations of space and geographical coordinates. So if you say, I have data in this weird projection on the globe, and my mesh is over here in maybe some other projection, then it knows how to evaluate values on that mesh. So we can specify components -1, just as it does in ordinary model specifications in R. It means don't include an intercept automatically. I will do that myself if I want to. Then I have a random field, and here is where it's really useful to not have to have the name of the component be the same as the input, because now I can construct a matrix of coordinates that were just stored in an easting and northing column. If I hadn't stored it as a proper geographical object, I can still just construct the matrix of observation locations. And if integration is involved later on, then at that point it will know what easting and northing is in terms of integration over space. So then it will create easting and northing points for the integration. So it can sort of deal with that to some extent at least. But if you have stored it as an SF object, which is what most people have now, for point data at least, then you just specify geometry, which is the column of an SF object that contains the actual geographical information. And in the linear model, you just usually you would have the response variable and what is now a general R expression. But the linear model is just the sum of the components. So the default, if you set a dot there, is to say, okay, take all the components and map them together. So that's the default. But if you want a nonlinear predictor, you just specify an R expression. And that can include calling functions that do something. You can have curly brackets and some temporary variables and compute things. And that turns out to be really useful because that means that we can construct new models without sort of changing the internals of anything. And if we have multiple observations models, now here is a relic that I regret using this name for this function. It's called light for likelihood, but it's not a likelihood, it's an observation model specification. Much of the Bayesian literature now is confused about that and call things likelihoods that are observation models. I have tried to repent and stop doing that. So there will probably be a sort of a synonym for that in this question. So this is what a model would look like in INLA. Lots of setup code just to figure out what are these matrices supposed to be. So INLA SPD make A computes the mapping between the coordinates and the basis functions, essentially computing the basis functions. And then you have INLA stat, which is a helper function that just adds NAs everywhere where INLA wants them. And then you have to call INLA stack data to extract the data and INLA stack A to extract the matrix. But all code like this essentially looks the same once you know what the model is. So in inlabru, just specify the mapper at most, unless it already by default understands what mapper you clearly need, because each model typically has one mapper that makes sense. Here, it can't know how we want to match individual years to indices 1, 2, 3, 4. So we just have to tell it, well, we take the set of years we have in the model, and then we create the mapper that indices into that set. So there we have to do a little bit of work, but otherwise, all of the messy work is gone. INLabru knows what to do. And ironically, if you then use a non-separable space-time model, that's a single model object, so the code actually gets shorter instead of longer. So here we just say that we have a predefined mapper for these types of models, and they take space and time, and you can give it whatever space and time information you have. So that's the idea, that these complex things should be easy. Now, of course, when you have real data, things get messy just because of that, but we try to at least help you on this in this part of it. So, I think I'll just quickly go through this example. So INLabru wasn't restricted to point processes, just where we started. So that's where we have the most of the examples. And this is one of them, which is, I think this is simulated dolphin data, but the transects are real. So it's when you take a ship across the Gulf of Mexico and look for dolphin groups. And you put a dot on the map where you find the dolphin group. And then you want to estimate the intensity field across space. So hopefully be able to estimate the total number of dolphin groups in the Gulf of Mexico. And ideally estimate the number of dolphins. But then you would also have to model the size of the groups. And groups of dolphins can merge and split. So it becomes messy. So I won't talk about that today. Just the simple part of the problem. So the point process likelihood doesn't look like our ordinary likelihoods because it involves aggregation over space. It's not a pointwise thing. It's not a single contribution for each observation. The observation in a point process is not the points, it's the space between the points. The fact that there were no points in this whole region and only points here that were observed. So the typical situation is this. We have a sum of the log intensities minus the integral of the intensity across the whole of space. So that's a bit annoying, but we can do numerical integration of that integral. So we just have to evaluate lambda at a bunch of locations in space, whether there are points there or not that we've observed. We're just interested in capturing all the possible variability of lambda across space, and space-time would also work here. But traditionally, this would then be a linear predictor, which then leads to a low Gaussian Fox process. You have a linear combination of Gaussians. But you don't see all the dolphins. If they're far away from their ship, you won't see them. So you need a model for what is the probability that you would see a group of dolphins if you knew how far away they were. And that probability will then decrease with distance. So eventually you get to a point where you can't see them at all, either because of the curvature of space or the wave heights are too big. So one of the models is this so-called hazard rate model, where you have parameters sigma and psi that control the spatial extent and shape of this detection probability model. And if you include that in the model, you get an intensity that is a function of location along the transects and the distance from the shift transects, with the intercept and field that we had before, plus the logarithm of that detection probability, plus log 2, because it could be either to the right or to the left of the shift orbit, port or starboard. So that's not recorded or not used in this. So this is nonlinear in sigma and psi. So we model sigma and psi as transformed Gaussians with no transformation, basically setting the priors for them. And then we linearize things, and off we go. So here we just have to specify that I have this, well, here this inverse of sigma, or the 1 over sigma, is a transformed thing, so to make that exponential. And the psi parameter is also, well, that's gamma distributed. And then we just go along as we are used to and specify the model. And here cut off the last bits in the slide, but what's missing there is to say that the domain is defined by this mesh that we define. So that's what it needs to integrate it. And then you can, well, after you run that, you could look at the summary statistics from it, but for spatial models, what I usually like to do is to plot the actual spatial field to see that there's nothing obviously wrong in terms of space. So then we can run predict, which is the thing that doesn't exist in INLA, but we made it for inlabru. So internally, it generates posterior samples and then just compute summary statistics. But it sort of partly knows about space, so it can make sure that you get the spatial object out in some situation. It makes it easy to plot. So then we can plot both the intensity field and the pointwise credible bands for the detection model. We can then do data level prediction, where we have a more complicated expression that we want to predict. We're integrating over space there. We have used fmint to construct an integration scheme, and then we use that integration scheme just to inside of the predictor. And we can do that for both the transects and for the whole study area. And we get different types of integration schemes. And finally, we can do things that you would usually, the easiest way to write code for these things is just do sampling for everything. But if you're sampling the intensity field and then sample the data level as well, then you have to do a lot of samples. But we already know the exact conditional distribution given the intensity field. So let's just sample the intensity field and conditionally that compute the exact thing. So that's a sort of Raoult-Blackwellized variance reduction method that you can use in regular MCMC as well. It's just that you usually don't for various reasons. But if you do, you can see the benefit of integrating over the posterior distribution for the parameters. If you just did a plug-in estimate, you get the red density. If you integrate properly over the whole uncertainty, you get the blue estimate. So clearly we need to worry about, or not worry about it, but we need to take into account all of uncertainty. And this one, unfortunately, I will skip. It's a pretty picture. Lots of slides. And finally, there are links both to INLA and inlabru. And if you wonder why it's called inlabru, is that when we're working on it, me and my postdoc, we had just moved to Scotland, and the other collaborators on the project were also in Scotland. And there's this soft drink R-INLA, and eventually we came up with the name just because we needed a name. So it's a Scottish influence. Thank you very much.